This last section, and I will talk Luis Marcio Salge. He will talk about Hardy inequalities on Hardy spaces revisited. Okay.
So, hi everyone. First of all, I would like to thank the organizing committee for being here today and have this opportunity. So, today I'm going to talk about Hardy inequalities on Hardy spaces. This is a joint work with Thiago Picon and Joel Cocaile from USP Ribeirão Preto. And in this work, Thiago found a paper about these Hardy inequalities on Hardy spaces, and he proposed to us to study this paper, understand the techniques used there, and propose a version for local Hardy spaces. That's why it's called Revisited. So, the main goal of this work was to study the Hardy inequalities. Actually, is a generalized Hardy inequality. So we have some constants here. So mi is between 0 and 1. Alpha is a natural number or 0. And R satisfies this relation with P and mi. And we have this inequality for quasi-norm on Hardy spaces. And this is the Hardy operator. So we studied a version also for local Hardy spaces. And some historical background about the inequality. So Hardy stated this inequality that it's the non-Hardy inequality, and he only proved it in 5 years later. He said he was mainly preoccupied with the version for infinity series. So we can formulate this inequality in a more general way using some parameters here, mi and alpha, as I said before, and this inequality becomes this inequality number 3 here. And we can recover the classical one with mi and alpha equals to 0. And also we can reformulate this inequality using G like this, and we have this inequality here, and it's possible to prove that it works for all G measurable positive such that C satisfies this relation and is finite. It means that the parameters there must satisfy these two inequalities. So the question is, what happens if P is between 0 and 1? We can say that for P equals to 1, the inequality doesn't hold for L1 norm, because we can take a test function with these properties, and for alpha equals to 0, if the inequality holds for L1, we should have this guy here. But it would mean that this equation here should be finite. But since the integral of the test function is not 0, we cannot have this finite. So, although the inequality doesn't hold for norm L1, we can do some progress. And Kwok-Pung in his paper stated this, that for Hardy distributions on HP with support in 0 infinity, we have the Hardy inequality, we can formulate the Hardy inequality in this way. So, first I'm going to talk about what are the Hardy spaces, some important properties of them, and the local Hardy spaces. The Hardy spaces are subspace of the temperate distributions such that the maximal function of f has LP norm finite. So for the maximal function, we can take a test function with these properties here, take a convolution, and take a sup for all t positive. And for the Hardy spaces, if P is between 1 and infinity, we have the classical LP, and H1 is a subspace of L1 with this property here. So also for the Hardy spaces, we have some special functions, which are called atoms. An atom is a measurable function that has support inside the ball that satisfies this that we call size condition and has moment condition. And also, in Hardy spaces, we can do what we call the atomic decomposition of the HP distributions. Every HP distribution can be written as a series with atoms and coefficients such that this guy here is finite, and this converges in HP quasi-norm, okay? The local Hardy spaces are very similar to the classical Hardy spaces, but for the local Hardy spaces, we take the maximal function with t varying between 0 and 1. So here we have some difference. For instance, the Schwarz functions is a subspace of the little HP here, but not of the classical Hardy spaces. And we have similar properties when p is bigger than 1, and we can see here that H1 is a little big than H1, classical H1, but is also in L1. Okay, in the local Hardy spaces, we also have atoms, but we have a difference here. The local atoms are supported in balls, have support in a ball, and satisfies the size condition. But we have a difference in the moment condition. The only local atoms that have moment conditions are the atoms that are supported in balls with measure less than 1. Okay? This will imply a big difference for the Hardy inequality in this context. Also, we have atomic decompositions for local Hardy distributions. Okay, the technique used to prove the Hardy inequality on global Hardy spaces are basically this. We decompose our function in even part and odd part, and if the function has support in 0 and infinity, we can write the function like this using only the even part, or we can write the function like this using only the odd part. We also can do this for distributions, temporal distributions with support in 0 infinity. So using this property, we define special types of atoms that are the alpha type atoms in R+. So in the global case, they are atoms that have the size condition, but the moment condition only works for this alpha here. And if we take a classical atom, we can change it to an alpha type atom in R+, writing the function like this. We only take, if alpha is even, we only take the even part of the original atom, and this guy here becomes an alpha atom of type alpha type atom in R+, and if alpha is odd, we write the function using only the odd part, and we get an alpha type atom in R+. So, first of all, he proved that for this kind of atoms, the Hardy operator is bounded, uniformly bounded on this type of atoms with the LR norm. To see this, first of all, we prove that the support of the image of the atoms are also in the ball that has the support of the original atom. To show this, we use the support condition and the moment condition. When we will see for the local case, this doesn't happen because we don't have moment condition for all atoms. And this will be important. So with this in mind, we can use Hölder estimative to estimate the module of this guy here, and we can calculate LR norm. So using that the constants satisfy this inequality, and using again the size condition, we have that our operator is limited, uniformly bounded on atoms. Because if I remind you that 1 over p is actually mu plus 1 over r. So this becomes, this exponent is 0. So after this, we can prove that our operator is bounded on HP distributions that are also LQ functions with support in 0 infinity. To do this, we used an approach by Pablo Rocha. So with the approach of Pablo Rocha, we take our distribution in HP and we can find a sequence of atoms such that the atomic decomposition holds and the convergence is in LQ. And then we can change these atoms. So if alpha is even, we change the atoms using the even part. If alpha is odd, we change the atoms using the odd part. And we can conclude that the atomic decomposition, in the atomic decomposition, we can use these new atoms that are alpha type atoms in R plus. So with this in mind, we can take a specific T that satisfies this equality. So the Hardy operator is bounded between LQ and LT, and we can conclude that the image of the distribution is actually the image of the operator applied only in the atomic decomposition. So we get this estimate, and we can do the estimate for LR. We only have to separate in some cases. First the case, well, R with R bigger than 1. So here we use this estimative, and here we use that the operator is uniformly bounded on the atoms, the alpha type atoms, and here we use that the HP quasi-norm is comparable with this norm, with this series here. And again, for the R between 0 and 1, we only have to be careful with this exponent here. We first do this inequality here using the same techniques. So first of all, use the boundedness on atoms, and then only that the quasi-norm, the HP quasi-norm is comparable to this series. So we can extend our operator to a subspace of the Hardy spaces. So we consider the closure of this subspace of the Hardy spaces, and we conclude that there is a unique extension of the Hardy operator to this closure such that we have the Hardy inequality. Okay, now we go to the local case. For the local case, we can do the same thing and define an alpha type atom in R plus. So it's the same way we did before, but here we need to remember that local atoms only have moment if the ball that contains the support of the atoms has measure less than 1. So, okay, if the atom has moment, it only has moment for this power of x, the power alpha. So again, if we start with a local atom, we can change it to a local atom of alpha type in R plus. So if alpha is even, we use the even part. If alpha is odd, again we use the odd part. So here we have a restriction that we didn't have for the global case, because here we don't have moment condition at all times. So if alpha is less than 1 over p minus 1, we can choose an atom such that the image of this atom is not even in LR. Okay? We need only to do some calculations here. We have to be careful choosing an atom such that this is not 0. So this part that in the previous case, the moment condition dealt with, here we don't have moment condition, so it goes to infinity. So here's a restriction that we didn't have before. Even though for, it's not the only restriction that we have here. Even for the alpha that could work, we can find a sequence of local atoms of alpha type in R plus such that this limit goes to infinity. So this operator is not bounded, uniformly bounded for these atoms. For alpha in this range, we can conclude that the image of all local atoms are bounded, but not uniformly. To see this, we only have to choose a special kind of atom here, just a simple function corrected by this constant to have size moment, size condition, and since it's supported in a ball in an interval with length bigger than 1, we don't need to have moment condition. And doing some calculations, we conclude that the norm, LR norm, for d to infinity is like this. So we can create a sequence of these atoms using dj and cj with these properties such that this norm is bigger than this guy here. And since this exponent is bigger than 0, it goes to infinity. Okay, so the original operator, the original operator won't work for the local case. But we can make some progress still. So what we did there at that time, we were trying to find an exponent here, so change the weight of the original operator such that we can correct this kind of problem in order to the integral converge. So we added some epsilon, minus epsilon in the exponent here and do the same calculations in order to have convergence for all atoms, uniformly bounded for all atoms. So we found out that this epsilon must also be bigger than 1 over p minus 1, and we can, changing this weight with this exponent, we get that for our atoms that don't have moment, the operator is uniformly bounded. Okay, so, but there was still a problem. This new weight works for the atoms that don't have moment, but they don't work for the atoms with moments. So we needed to find a hybrid operator to work for the both atoms. So what we did there was to mix the two operators in this minimum here. And we defined this now operator version of the Hardy operator for local Hardy spaces. It's the same operator with this minimum here. And we could conclude that this operator now works for the local atoms. So in order to prove this, we only have to check that this operator works for the local atoms that don't have moment. Because since it is the minimum between the both operators that we find here, we only need, it already works for the atoms with supported in small balls because they have moments. So for the atoms that don't have moment, we divided the norm LR in two parts. First, the part from C to D, and then D to infinity. D to infinity, we can use the T alpha mi epsilon with the new weight. So here we have a convergence in the uniform bounds. And this guy here is the previous operator defined in the beginning, the original one. So here it works okay. The problem with them is in D to infinity. So with this, again, we use Holder inequality, and we can do the same calculations we did before, now for general atoms, and we can conclude that this part here, that was the problem for the atoms that don't have moment, is uniformly bounded. So this new operator works for all atoms of the local Hardy spaces. Okay, so we can again use the Pablo Rocha technique to, it's in the same way that we did for the global Hardy spaces. We can use again the Pablo Rocha technique to prove that for HP distributions, intersection with LQ, with support in 0 infinity, we have the Hardy inequality, but adapted with this new operator here. Okay? And again, we were able to do the same, consider the closure of this intersection, and conclude that there's a unique extension of this adapted Hardy operator on local Hardy spaces such that the Hardy inequality works. And now we are trying to work if there's another weight that we can put here that is not a power of x, that also works, but it's still work in progress. And that's what I have to show to you today. Thank you very much.